Okay, so welcome all of you to the class. So this is week 7, live interactive session. Okay. And my name is Shubham Rai, and I am a PhD research scholar in Department of Applied Mechanics, IIT Delhi. So let me start. So in week 7, you would have studied linear momentum balance in cylindrical coordinate system and stress and strain relations in cylindrical coordinate system. Let me just write. So you would have studied linear momentum balance in cylindrical coordinate system. So this was the first topic, and then you would have studied stress strain metrics. So strain metrics in cylindrical coordinate system. And you would have also studied stress strain relationship in cylindrical coordinate system. Okay. So now let me recapitulate the concepts that you would have studied in the class. So first is LMB or linear momentum balance in cylindrical coordinate system. Okay. So so you know that you have done linear momentum balance in cylindrical coordinate system. So what we need to do, we need to uh, do that external force is equal to rate of change of linear momentum. That is a linear momentum balance equation. So external force may comprise of traction force and body forces. So let me just write. So external force can be from traction and body force, and this should be equal to rate of change of linear momentum. So let's say you have this linear momentum. Okay. So where your Ft is total force due to traction, and Fv is total body force, and then you have rate of change of linear momentum, which is equal to, I mean, this is dp by dt, which is rate of change of linear momentum. Okay. Then in the class, that has derived the components of this traction force. So it will have component in the z plane. So traction will be there on the z plane, on the r plane, and the theta plane. So let me just write all the three components, that is on the z plane, on the r plane, and on the theta plane. Same color. So f fraction that will be given by on the z plane first I'm writing. So that will be del sigma zz divided by del z, and this will be in z direction, plus del tau theta z by del theta by del z actually. So we are moving in z direction only. So then this will be e theta plus del tau rz by del z, and this will be er. This will be in direction er. So this is the first. These are the first three components, and these are on z plane. Let me just write here. This is the equation corresponding to z plane. So this is traction force on the z plane, right? Then you have r plane. So let me just write that also. So plus del sigma r r over del r plus sigma r r over r, and this will be in direction er, plus del tau theta r by del r plus tau theta r by r, and that will be e theta plus del tau z r by del r plus tau z r by r, and that will be in direction ez. So this is on r plane. I'm just recapitulating. I'm just writing the formula. The derivation has been done in the lectures. You can go back there and watch the derivations. So this is on r plane. This both. So we can say that this is on r plane. Now we have third component on theta plane. So let me just write first. 1 over r del of 2 r theta by del theta minus sigma theta theta over er plus 1 over r. So r theta is well sigma theta theta over del theta, and this will be in the direction of theta plus del tau z theta over tau theta, and Ez, and this was multiplied by delta V. And there were higher order terms of V also, so that is higher order terms of delta V. Delta V is obviously the infinitesimal volume of the small cylindrical element that we have taken. So the last three terms are on theta plane. So these terms are on theta. So we are able to see that the terms which are on z plane, so only stress components involving z direction. So you know that from the Cartesian coordinate we concluded that second indices of stress denotes the plane normal, right? So that's why here the second indices is z. So this is denoting the z plane. So these all stresses are on z plane. Okay. So and similarly the second set of terms. So these have r as the second indices. So these all stresses are on r plane, and similarly third set of terms have theta as second indices. So that's why they have they are on theta plane. So that means I'm just writing these equations as, let's say this is ft, the force due to traction vector. So this is equation number one. Now let me write body force. The body force is simple, that let's say we have VR in the radial direction and v theta in theta direction, angular direction, plus Vz in z direction. So these are the three components of the body force along different directions multiplied by delta V because body force is always force per unit volume. I mean, in this case, it is force per unit volume. And then you have order of higher order volume terms, right? Higher order terms of delta V. So this is this equation number second. And then you have rate of change of linear momentum, which is d by dt of P. So P, P is mv and m can be written as rho into V. So this is essentially d by dt of rho into volume into velocity. So we assume that density is not changing with respect to time, neither the volume is changing with respect to time. So we are considering a fixed volume. When we are doing the analysis, it is not changing with respect to time. So that's why this equation, and when we differentiate acceleration, velocity with respect to time, it will be acceleration. So the equation will result in um, rho into volume times acceleration, something like that. So rho will remain as it is, and acceleration will have three components, that is radial component plus angular component plus z component. And we have small, I mean, delta V is this volume of the small cylindrical element that we have taken. And then higher order terms of delta V will be there. So this is the third term. Now, if you combine all these terms, got equation number 1, 2, 3, and if you put in this equation here, so you get final equation of linear momentum balance. I'm just writing the final equation. So I write like I'm just writing first LMB in R direction, LMB equation. R direction. So that will be del of sigma R over del R plus 1 over R del of rho R theta over del theta plus del of 2 R Z over del Z plus sigma R minus sigma theta theta divided by R plus R. Okay. Plus BR is equal to rho AR, rho intensity. So what we have done is we have divided this whole term with this infinitesimal volume. So this infinitesimal volume will disappear, and this higher order term uh, will be divided by the volume, and then still there will be some volume term left because these are higher order in delta V. So and then this when this delta V will approach to zero, these terms will disappear. So that's how you will get this equation. So this equation is in R direction. Similarly, there will be LMB in theta and Z direction. So let me write that. So we write LMB equation theta direction. So that will be del of rho theta R over R plus 1 over R del sigma theta over del theta plus del of tau theta Z over del Z, and some extra terms will be there. This will be price of tau R theta by R plus B theta will be rho A theta. And then you have LMB equation in Z direction. So here you have del of sigma R over, and it will be R over actually. Now first we will start with tau ZR, so RR will not come here. So del of tau ZR over del R plus 1 over R, del of tau Z theta over del theta plus del of sigma Z Z over Z del Z plus tau ZR over R plus BZ is equal to rho AZ. Now you have written LMB in all the three directions. So if you see this R del theta is nothing but it can be interpreted to be y direction. So let's say you have x, y, z direction in Cartesian coordinate system. Here you have r theta in z direction. So r is some direction, and this theta is since it doesn't have any units, so that's why we have written r del theta. So if you remember cylindrical coordinate system, so r del theta will be nothing but it will be distance along some arc. So that will be along theta direction. R del theta is something infinitesimal distance along theta direction. So you are differentiating with respect to that infinitesimal distance, and you understand what is Z. Z is along the axis of the cylinder. Now these terms are this term is extra term here because these terms are similar to the Cartesian coordinate system that you had. So del sigma xx by del x plus del sigma xy over del y plus del sigma obviously tau, obviously del tau xy over del y plus del tau xz over del z. So this was there. So but plus bx is equal to rho ax. So this was in Cartesian coordinate system, but this term here is extra term in cylindrical coordinate system. Similarly, if you see the second equation, then you had all the terms that time as well. So let me just see. Here actually it should be del zr, what I had written. Okay. Then it is fine. So this term is extra term here. Other than that, these three terms are same as, I mean, it's not same, but it's similar. So it is similar to Cartesian coordinate system. And now you have this, in the third equation, you have this as the extra term. So let me just underline. You have this extra term here, this extra term here. Other terms are similar to the Cartesian coordinate system. Let me now write the same matrix in cylindrical coordinate system. So let's choose some different color. Then you have main matrix in cylindrical coordinate system. So if you see, that is nothing but strain tensor, which is given by half of grad u plus grad u transpose, right? This was your strain tensor. Now you want to write your strain tensor in cylindrical coordinate system. So you need to substitute your u as, so your u now will be ur er plus u theta e theta plus uz ez, right? And use the if you use the definition of gradient in cylindrical coordinate system, so finally you will get these this matrix. It is a metric because this is a second order tensor. Gradient of a vector is a second order tensor. So, so let me express this strain tensor, and this is given in. Let's say firstly I'm writing in Cartesian coordinate systems. If I write in Cartesian coordinate system, so it is given in Q3. So this will be given by del u1 by del x1. The second term will be half of del u1 by del x2 plus del u2 by del x1. And this will be half of del u1 by del x3 plus del u2 by del x2. So del u3 by del x2. Right? And since it is symmetric, so this term will be similar to first row and second column term. So it will be del u1 by del x2 plus del u2 by del x1. You know this is will be del u2 by del x2. And here you will have half of del u2 by del x3 plus del u3 by del x2. Right? Then it is symmetric. So here also you will have del u2 by del x3. Sorry, del u1 by del x3 plus del u3 by del x1. And here also you have del u2 by del x3 plus del u3 by del x2. But here you will have del u3 by del x3. Right? So this is the matrix that you have. Now this is in Cartesian coordinate system. Now if you try to write in cylindrical coordinate system, so you will have strain tensor in r theta z coordinate. You can also add er e theta ez. So here you have first term, which is del u r by del r. Okay, so this is in radial direction. Second term is half of 1 over r um, del u r by del theta times u theta. Okay, plus del u theta by del r. This is the second term. And third term will be half of del u r by del z plus del u z by del r. Right? And then here also this will be symmetric, so it is similar to the term written in first row and second column. It will be half of, I can just write it like this also. Actually, there is a mistake. Minus. And here you have 1 over r del u r over del theta minus u theta plus del u theta over del r. This will be your square now. Now you have this term, next term. So this is 1 over r del u theta by del theta plus u r. So there are some extra terms. So like this u r by r is an extra term in this stream. Here also this minus u theta by r is the extra term. So you can refer to lectures to understand the meaning of these extra terms, why these extra terms are arriving. Mainly because here your e theta and er direction changes with theta. Things are not constant with theta. Whereas in Cartesian coordinate system, you have your coordinate system direction does not change with space. Means z is going to be x is going to be in this direction only, y is going to be in this direction only, and z is going to be in this direction. If vary in space, the direction is not going to change. Whereas here, this is not the case. Here, er and theta changes with direction. So let me write the third component. So 1 over 2 del u theta by del z plus 1 over r del u z by del theta. Let me write the last row. So 1 over 2 del u r by del z. This is del u z by del r. Then this is 1 by 2 since it is symmetric. So this will be del u theta by del z plus 1 over r del z by del theta. And this is del z by del z. And this is your strain matrix in cylindrical coordinates. So let me just write physical significance of strain terms. So here I just call physical significance of epsilon r. And you can say that it is called longitudinal strain or radial strain. Okay. And the value is known, value is different r, so that is, we have this. So in radial direction, you will have some strain. So this strain is represented by epsilon r, and this is nothing but the strain tensor in ER direction. That may give you traction on R plane and then rotate in ER direction, so that will give you epsilon r. And that is nothing but insert the strain tensor here, multiply with ER vector and dot with ER, so you get epsilon. This first component, first row, first column, then you are good enough. Now you have significance of epsilon theta theta. So this strain is also called hoop strain or circumferential strain. So in a cylinder, let's say you are inflating some cylinder. So when you are inflating, its circumference will increase. So associated with that increase in circumference, there will be some circumferential strain. So let me just write the expression for that. So you have epsilon theta theta. So that is nothing but if you find traction on theta plane and then dot in theta direction, find the component of that traction vector in theta direction. So you get epsilon theta theta, and its expression is 1 over r del u theta by del theta plus ur. So you have this ur by r as some extra term that will come in cylindrical coordinate system. So we can say that um, this is called, this strain is called as hoop strain or circumferential strain. I'm deciding that. Called as hoop strain or circumferential strain. And actually it denotes elongation of any line element along theta direction. Let me write that as well. So here it represents elongation of a line element directed along theta direction. The line element is along theta direction, so and its elongation will be given by this string. So now coming on to the significance of gamma r theta. So So gamma r theta, you know that it is shear strain. Shear strain on theta plane in r direction, right? Because this is second column represents the plane direction. So this will be shear strain on theta plane in r direction. So that's right. So gamma r theta is twice of epsilon r theta. And this will be given by twice of epsilon r theta is given by, firstly you will take traction on, so this is on theta plane in r direction. Mostly you would like to find out traction on theta plane. So we have epsilon theta, and in direction ER. This will be your this. So this level of, we are taking the strain tensor, and actually this will not be a traction because we are dealing with strain. Sorry. Yeah. So we can say that it is some kind of vector. Okay. So since it is symmetric only, I can write anyway. So I'm just writing epsilon, so that this will be on theta plane and in our direction. So this is a strain. So pardon that. I think from some time I was calling it traction. This is known as traction, but it will be component of strain. So here also it will be a vector of a vector in r plane and its projection along r direction. Similarly, this will be some vector on theta plane and its projection along theta direction. Here, this denotes, so obviously the second indices denote plane normal, right? Because column number or second indices denotes the plane normal. And this first denotes the direction. Okay. So that's why consistent with this definition, the strain tensor, we want its component on theta plane because we have theta plane here. So that's why we have multiplied this tensor with this p theta vector. So it will give components of strain tensor on theta plane. That will be vector, and its component along r direction on that plane will give you gamma r theta. Anyway, so this will be given by 1 over 2 del u r by del theta minus u theta plus del u theta by del. So there is some mistake. Here there will be 1 over r as well. So let me just write. This will be 1 over r, or you can say 2 over r. I'm just taking. So we want to write gamma r theta, right? So r theta is, this will be the component. So this 2 will disappear because we are multiplying with 2. So we will have 1 over r del u r by del theta minus u theta plus u theta by r. So here you will have 1 over. This 1 over 2 will disappear because we are multiplying by 2. This will be the final expression. So let's go to the next concept, which was stress strain relation in cylindrical coordinate system for isotropic material. So it will remain same only because for isotropic material, stress strain relation does not changes with direction. Means You can choose any three normal directions, any three set of normal directions, and stress relation will in those directions will be same. So let me just write stress strain relation in cylindrical coordinate system. For isotropic material, right? So if I try to write it, so first, we will have first epsilon theta theta. So this is given by 1 over E, same thing. Sigma theta theta minus, you can just write it down by yourself also. This is sigma RR plus sigma ZZ, right? And then you have epsilon ZZ, that will be 1 over E, and sigma ZZ minus mu times sigma RR plus sigma theta theta, right? Then you have epsilon RR over E sigma RR minus mu times sigma ZZ plus sigma theta. Then you have shear strain, so you have gamma R theta. So this is given by tau R theta divided by G. And then you have gamma RZ, it will be tau RZ by Z. And then you have gamma theta Z, so it will be tau theta Z. Okay, so this will be the stress strain relation in cylindrical coordinate system for isotropic materials. Nothing has changed. Everything here the same. One thing I would like to change here. This is looking like new, but this is not new. This is gamma. And here this is new. And new and gamma looks almost same. Pardon for this kind of confusion on plating. Okay, so let me go to the problems now. If you have any questions, you can ask me from this recapitulation. Let me go to the problems. So you have problem one. Yeah. So let me write the problem screen. You have to verify that the following stress field satisfies the Z equation of equilibrium. In the absence of body force, to verify that the following stress field will be given to you now. So you have to verify the following stress field satisfies the Z equation of equilibrium in the absence of body force. Now the stress field is given by sigma RR to A over Z by R cube, Z by capital R cube minus 3 small r square Z over capital R to the power 5. This is the first sigma RR is given to you. Now we have sigma theta theta. This will be given by A Z over capital R cube And then you have sigma z z, that is given by minus a over z by r cube plus 3 z cube by r to the power 5. Then you have tau rz as well. So tau rz, so that is something but minus a times small r divided by capital R cube plus 3z square small r divided by capital R to the power 5. Then you have tau r theta, that is equal to tau z theta, and both are 0. And there is a relationship between capital R, small r, and z. So capital R is equal to small r square plus z square. This is the question. You have to verify the following stress field satisfies the Z equation of equilibrium in the absence of volumes. So solution obviously you have to only differentiate. So I'm just writing. We have to satisfy all three stress equilibrium equations. So firstly, I'm writing stress equilibrium equation in Z direction. So let me just write the Z equation of equilibrium in cylindrical coordinate system. So what is that? You remember? So there is nothing but del of tau Z R over del R plus 1 over R del tau Z theta over del theta plus tau. So this is extra term which I'll write later. So del sigma z z over del z plus this is the extra term that is tau z r over r, right? Plus rho bz, and there is no acceleration. Body is not accelerating, so that is 0. And this body force is also given to be 0, right? And this tau z theta is also given to be 0, so that's why its differentiation will also be 0. This will not be r theta, this will be z theta because we have taken z coordinate equation. Okay. So this the z theta is given to be 0, so this will also be 0 because it will not have any gradient with respect to theta because it is always 0. Now we need to find out del. So this first term, the second term, and this term. So let's find it out. So first we need to find out del tau z r over del r. So this tau z r will be equal to tau r z. So let me just so del tau z r over del r. So we have to differentiate with respect to small r, and then please remember this capital R is also a function of small r. So beforehand only I want to find out what is del of r by small r. So that will be nothing but I think r by r, small r by capital R. In this differentiate and check. And then I also find out del of capital R by del z. So that is nothing but z by capital R. So I use these partial differentials in my derivation. So I'm differentiating del tau z r over del small r. So this is the expression, and I have to differentiate this expression with respect to small r. So firstly, here I have to apply product rule. Firstly, I'll differentiate here small r, so that will be 1. The minus a is a function which will remain as it is, and this will remain 1 over r cubed. And then I will keep R as it is and differentiate this capital R with respect to small r. So then it will be minus of um, 3r by r4 and del of capital R with small r. Right? Yeah. And then you have z term. So then I'm applying again the product rule. So we will have 3z square. The small r differential of small r with respect to small r will be 1 and then r5. Then plus I'll keep small r as it is and then differentiate z square term with respect to small r. So it will be 6 z r over capital R to the power 5 and del z by del small r, right? And then plus I'll have to it will be minus because I have to differentiate this capital R is power 5 with respect to small r. If I do that, so I will get 15 z square r over capital R to the power 6 and then del of capital R over del small r. Right? So this is finally what I'm getting. Plus, yeah, it will be 15 because 5 will come from here and 3 is already there. So okay. So let me put the value of capital del of capital R by small r and del of capital Z by small r. So if you do that, so it will be minus of A and then 1 over r cube minus. So this term here is nothing but small r by capital R. So if you do that, so small r, so it will be 3r square by r to the power 5 plus 3z square over r to the power 5 plus del z by del r will be, I think this will not be there because z is not a function of r. So here this term will be 0 uh, because r and z are independent and capital R is dependent on r and z. So differentiation of small r, so differentiation of z will split to small r will be 0. And because these are not dependent on each other. So this term will not be there. So finally we have here we have minus. So 15 z square will remain as it is. And here will be r square over r to the power 7. I think this is all. So you have calculated this first term. Now you have to calculate del sigma zz over del z. So del sigma zz over del z will be calculated from this equation here. Let's calculate that. So del sigma zz over del z, so that will be minus of a, and then I'll have to differentiate. First it will be 1 over r cube, then you have to differentiate, keep z as it is and differentiate r with respect to z, so that will be minus 3z over r to the power 4, and then you have del of capital R by del z, and then your second term. So you have plus, to differentiate with respect to z, so you get 9z squared over r to the power 5, and now you have to keep z as it is and differentiate with respect to r is power 5. Differentiate r is power 5 with respect to z, so that will be minus of uh, 15 z cubed over r to the power 6, and here you have del of capital R by del z. Now if you substitute the value of capital R by del of capital R by del z, so that del z, so that will be capital Z by R. So if you substitute, you will get finally minus a times 1 over r cube or minus. So this will be capital R by Z. So 3 over r cube, right? Um, it means, okay, I'm sorry. So this will be z by r, not r by z. So then it will be 3z square over r5 plus 9z square over r5. Am I doing some mistake? No, I think it is right. Okay, so minus 15 z4 over r7. And you will get this. Only you have to do here you have to substitute z by r of this equation. So if you do that, so one order of each term will increase z square by r5. This is already 9 z square by r5, and here you have. Now you have every one more term left, I think. Yeah, this del tau. This is not a, there is not any partial differential in this term, so we'll have tau zr by r. So let me just, tau zr you already have this one, right? And if you divide it by, the step will divide it by small r. So if I write tau zr by r, so let's write that means minus a over 1 over r cube plus 3z square over r5. Now we have this tau zr by r here. So if you add all these three terms, the first one is this term here, second this and third this. Because these are the three terms in your differential equation, you should get 0. So let me just add and see. So what you have to do is you have to do del tau zr by del r plus del sigma zz over del z plus tau zr over r. We add all these three terms. Let me just add. So first one is this minus a times a will be common from every term. So I'm just writing this first term here. So this will be 1 over r cube minus 3r square over r5 plus 3z square over r5 minus 15 z square r square over r7. Right? And then you have to write this term here. If I write this term, so since I've taken minus a as common, so minus a will be common from this term also. So finally you get 1 over r cube minus 3z square over r5 plus 9z square. So it will be 6z square over r5. So here I'm combining these two terms, so it will be 6z square over r5. 9 minus 3, 6z square over r5. So I'm just writing here. And then you have minus, sliding below, 15 z4 over r7. And then you have plus 1 over r cube. I'm just writing to zr by r. So it will be 1 over r cube plus 3z square over r5. This will be the final. Now let's see how we can further simplify. So um, okay. So you have 1 over r cube here, 1 over r cube here, 1 over r cube here, and 1 over r cube here. So it will be 3 over r cube. I'm just writing here 3 over r cube, and then you can combine all the r5 terms. So here you have 3r square by r5 and 3z square by r5, 6z square by r5. and 3 z square by r5. So I think 3 z square by r5 plus 3 z square by r5 will be 9 z square by r5. And then you have minus 3 r square by r5. Okay. And then you have 6 here also. So 9 plus 6 will be 15. So it will be 15 z square by r5. Okay. And you have minus 3 r square by r5. So let me just write. Hmm, Just writing this term as it is 3 r square over r5. And then I'm taking, I think I have mentioned. Okay. Let me simplify. And minus 3. Okay, let me just combine these terms. So 3 z square by r5, 6 z square by r5, and 3 z square by r5. So here you have 6 plus 3 plus 3, 12. We have plus 12 z square by r5 here. And you will be left with, here this term is as it is. So you have minus 3 r square by r5. Deciding here. Then you're left with these two terms. So these two terms are left. You can just combine this also. Just writing them at the last. So here you have minus 15 z square r square over r7. Then minus 15 z4 over r7. So this is what you have. Fine. So I'll use this relation here, this relation which is given. But capital R square is small r square plus z square. So let me use. So if I use that, well, let me show you how I can use this. So minus a 3 over r cubed. So let me firstly take something common from here. So let me 12z square over r5. Actually, this will boil down to 0. There are some adjustments required. I'm just doing that. So 12z square over r5 minus 3r square over r5, capital R5, minus if you take 15 z square over r to the power 7 common. So you will be left with um, r square plus z square. Okay. So here you can substitute r square plus z square as capital R square. So you get finally minus a 3 over r cube 12 z square over r5 minus 3r square over r5 minus. So this will be capital R square and this will be cancelled. So you get minus 15 z square over r5 finally. So this 12 z square minus 12 z square by r5 minus 15 z square by r5. So you get minus 3 z square by r5. And then you can take minus 3 as common. So still, so here you have 3 over r cube and then you have minus 3r square over r5 and then you have minus 3 z square over r5. And if you take minus 3 common, so here you have minus a 3 over r cube and you can take minus 3 over R5 common. So you will get R square plus Z square here also. And this R square plus Z square is capital R square. So if we substitute, so we get A over 3 over R cube minus 3 R square over R cube. That is 3 R square over R5, which means 3 over R cube. So that will be 0. So first, we have satisfied equilibrium equation in Z direction. Okay. Similarly, we have to, okay, in this question, you only need to do that only. So you have to satisfy the Z equation of equilibrium in the absence of body fields. So we have done it successfully. So you just have to differentiate carefully and then use this relation. So finally, you'll get this equation as 0. So let me go to the next question. So next question says, so given the following stress field, in cylindrical coordinates, so one more stress field is given. So the stress field is given by sigma r, that is minus 3p z r square over 2 pi r to the power 5, capital R to the power 5. Then you have sigma zz is equal to minus 3pz cube over 2 pi r to the power 5. And then you have, so rz equal to minus 3 pz square r, the small r, over 2 pi capital R to the power 5. And then all other stresses are 0. Sigma theta theta is 0. And so r theta is also 0. And then we have tau z theta, that is also 0. And then we have this relation here as well. Capital R square is equal to Z square plus small r square. Okay. So what you have to do is you have to verify that the state of stress satisfies equation of equilibrium in the absence of body force. Okay. So let me firstly write equilibrium equation in this way. So given the stress field, you have to verify that state of stress satisfies the equation of equilibrium in the absence of body force. So there is no body force. Firstly, let me write equation of equilibrium in r direction. So this is solution. Let me take r direction. If you take r direction, so you have del sigma r over del r plus del tau r theta over r del theta plus del tau r z over del z. And you have one extra term which is plus sigma r minus sigma theta theta over r. So just differentiate and put the values. So I'm differentiating this del sigma RR by, so let me just do that. So if I do that, so we have del by del R, I'm just putting the value of del sigma RR. So if I do that, so this will be nothing but minus 3p z r square over 2 pi r to the power 5 plus delta r theta to r theta is 0, so this term will be 0. Right to rz, so to rz is given to you, so this will be del by del z, and this will be minus 3 times p z square r over 2 pi r to the power 5 plus, then you have sigma rr, which is sigma rr by r. So if you do that, so you get minus of 3p zr over 2 pi r to the power 5. Then you have minus of sigma theta theta by r, so which is 0. Okay. We have to prove that this whole term is 0. So let me just differentiate. So we have to apply product rule. So here minus 3p over 2 pi is constant. So I'm taking this outside. So minus 3p over 2 pi will be outside. And here, what will you get? So firstly, you will differentiate small r. So z is independent of small r. So z will come outside, and then you differentiate small r square. So this will be 2zr over 2 pi r to the power 5 and plus. Then you have to differentiate this capital R to the power 5, which will be minus of 5 z r square over capital R to the power 6, and then you have del of capital R over small r. Okay, this is what we will get from the first term. Then plus second term, so again minus 3p over 2 pi will be common, so I'm just writing it here. 3p over 2 pi will be common, and again you have to differentiate, so you get 2zr over 2 pi r to the power 5, and then you have to differentiate this capital R to the power 5 with respect to z. So again, you'll get minus 5 z square r over, oh, 2 pi I have taken outside, and it's just, so I need to write this. Yeah. And here the will be 15. Okay, 3 also I have taken outside, so only 5 only. So minus 5. Just checking. Okay, this is fine. So here you will get uh, minus 3p over 2 pi you have taken outside, so you get minus 5 z square r over r to the power 6, and del of capital R over del z. Okay. And then finally you have the last term minus 3p. I'm just writing here only, so minus 3p capital Z small r divided by 2 pi capital R over R. So let me simplify. So if I simplify, so actually you can take minus 3p over 2 pi common from all the terms. So I'm just taking this to be common term. So 3p over 2 pi is common. Now if you, I'm just combining all the terms. So here you will get 2z small r over capital R to the power 5. Yeah. And then here substitute del capital R over del small r. So that will be small r by capital R as done in the previous question. So small r over capital R will increase the, so this 5z r cube over r7 it will be, right? And then we have taken minus 3 over the common from the next term also. So first term will be plus of 2z r over capital R to the power 5 minus, and then this del of capital R over small z. That will be small z by capital R. It will increase this z cube, so z cube over capital R to the power 7. And then you have last term, which is minus of. So it will be plus because you have taken minus CPOT by as common. So finally you will have capital Z small r over r to the power 5. So in doing so, we have used this relation that capital R over small r, nothing but small r over r, and then capital R over del of small z is capital Z, whatever it is. It will be z over capital R. And again, you can take z square plus r square, I think as common. So if you do that, so then z square plus r square will have to. So let me combine all the r to the power 5 terms and all the r to the power 7 terms. So you have this r to the power 5, r to the power 5, and r to the power 5. So this is 2zr and this is 2zr, 4zr plus zr, 5zr. So finally you will get minus 3p over 2 pi. And then here you will get 5zr over r to the power 5. And then here you have r to the power 7. So which is minus 5 as we get 10. So we get minus of 10. Um, then will this be 0? Am I missing something? Or let me just check. So I think this is fine. So okay, this is fine. So to combine this, I'm taking, so this will not be 10 because the numerator is different. So I'm taking 5zr or r7 to be common. So if you do that, so 5zr over r7, if you take this to be common, so from these two terms here, this term and this term. So in the brackets, you will get r square from the first term, first yellow term, and z square from the second. That is fine. It will not be 10 because numerators are different. Okay, so minus 3p over 2 pi, and then capital 5 zr over capital R to the power 5 minus r square plus z square is r capital R square from here, from this equation you can see this equation here. So that was substitute. You substitute, you will get here 5 zr over r to the power 5. So this will be 0. So we have satisfied the stress equilibrium equation in r direction. So let's go for theta direction. If you go for theta direction, so stress equilibrium equation in theta direction, so that will be given by using different colors. So we have theta direction now. If we take the theta direction, so that will be given by del of tau theta r over del r plus del of sigma theta theta over r del theta plus del of tau theta z over del z. Then you have one extra term which is twice of tau r theta over r. So if you see all the theta terms, I think are zero. So this is zero. This is also r theta is zero. Tau z theta is zero. And that's why this will automatically be zero. So here this term will be zero. This term will also be zero. This term will also be zero, and tau r theta is also zero. This is automatically satisfied. Okay. Now we have a stress equilibrium equation in z direction. So if we write that, so in z direction, you will get finding, and let me just write here z direction. We write in that z direction, so we have del of tau zr r z zr over del r plus 1 over r del of tau z theta over del theta plus del of sigma zz over del z plus you have an extra term del of tau zr over r. And it will not be del, it will be tau zr over r plus rho bz. Obviously body force is not zero, so I'm not writing this term, so this should be equal to 0. So out of that, the second term is automatically satisfied because here the second term, because tau z theta is 0, so this is automatically satisfied. Now let me put the expression tau zr and sigma zz. So tau zr is this one and sigma zz is this one. So if I use these expressions, so sigma zz is minus 3p cube z. Yeah, p cube z. So this will z minus 3p cube z over 2 pi r5. So let's put that. And you have to differentiate this with respect to z. And then you have the first term tau zr over r. So tau zr is this minus 3p z square r over 2 pi r5. And you have del over del r. And then you have extra term tau zr over r. So to do that, so tau zr over r will be given by this is pz cube of p cube z. This is pz cube. And let me just verify. So this is minus 3pz square over 2 pi r5. So this is equal. Okay, now we have to tau zr over r. So this will be here there will be minus sign. And since you have this tau zr, and if you divide by r, the small r will disappear. So here you will have 3p over 2 pi and z square over r5. So this you have to prove equal to 0. Okay. Let us do that. So you have to differentiate. So firstly, I'm taking minus 3p over 2 pi as common. So now if you differentiate first term, so you get um, the square z square over so z is z and r is r dependent. So firstly, I'm differentiating r, so we'll get z square over capital R to the power 5 plus now r will remain as it is. Actually, it should be a minus and then 5 um, z square r over capital R to the power 6. And then here you have del of capital R over del of small r. And from here also, since I've taken minus 3p over 2 pi as common and I'm differentiating with respect to z. So here you will get um, minus 3p over 2 pi has been common, so it will be plus of 3 z square over r to the power 5. And then you differentiate r is z, so this will be minus of 5 z cube over r6 and del of capital R over del z. And then again you have plus of, because minus 3p over 2 pi have common, z square over capital R to the power 5, right? So I'm just combining all the terms now. So this capital R over R will be small r over r. So this will be, so I'm just substituting here. So this value here will be small r over capital R, and this value here will be z over capital R. So if you substitute here in the equations, let me write in the next line. Finally, minus 3p over 2 pi if you substitute in the equations. So z square over capital R to the power 5 minus. So you will get 5 z square r square over capital R to the power 7 plus 3 z square over r to the power 5 minus 5 z to the power 4 over r to the power 7 plus z square to the power. And if you simplify these terms, so here you have z square to the z square divided by r to the power 5. So this will be 5z square by r to the power 5. And then from here, actually, from this term, you can take, I think, minus 5z square over r7 common. So if you do that, so let me just 3p over 2 pi, and then here you have 5 z square over r to the power 5, right? And then here you can take 5 z square over r to the power 7 as common. Finally, from the first red term, so we will get r square, and from the second one you will get, and you know that r square plus z square is capital R square. So finally, so this is going to be capital R square, and R square by R7 will be R5. So these terms will be 0, because here you have 5z square over R5. Here also this will be 0. So in this way, we have satisfied equilibrium equation in all the three directions. So we just have to differentiate carefully and use this relation and these differentials. Okay. So let me drink some water, then we will go to the next problem. Okay, so let me go to the problem number 3. So it says, given the following stress field, in a thick cylinder, in a thick wall elastic cylinder, and stress field is sigma r is equal to A plus capital B by small r square, and sigma theta is given to you, that is A minus B over small r square, and all the other terms are 0. So tau r theta is equal to tau r z is equal to tau theta z is equal to sigma z z. These terms are 0. And here A and B are constants. right? So what you need to do is you need to firstly verify that the given state of stress satisfies equations of equilibrium in the absence of body forces. Right? First, you have to prove that. Then, in the second part, you have to find the stress vector on a cylinder surface. On a cylindrical surface, R is equal to A. So at R is equal to A, you have to find the stress vector on the cylindrical surface. And in part C, we have to, so in part C, if the surface traction on the inner surface, R is equal to Ri, the surface radius is Ri, is a uniform pressure Pi, and the outer surface, and the outer surface radius, outer surface, the outer surface is given by R is equal to R naught, right? Is free of traction. Outer surface is free of surface traction, and to find constants A and B. Constants capital A and capital B. So, given the following stress field in a thick wall elastic cylinder, we verify firstly that it satisfies stress equilibrium equations. Secondly, you have to find some stress vector on a cylindrical surface with radius r is equal to a. And the third part, if the surface traction on the inner surface whose radius is r is equal to ri is the uniform pressure pi, and the outer surface r is equal to r naught is free of traction, we have to find the value of constants a and b. And this is like the third part is like boundary condition. So let me do the solutions. Firstly, we know that tau r theta is equal to tau rz is equal to tau z theta is equal to sigma zz. All are zero, right? The only non-zero terms are sigma rr and sigma theta theta. And also sigma rr is only function of r and sigma theta theta is also only function of r. So all the other stress equilibrium equations are already satisfied other than the equilibrium equation in r direction. So equilibrium equation in theta and z direction are already satisfied because all the terms are zero and none of the terms are function of theta and z. So we only need to satisfy stress equilibrium equations in r direction. So let me do that. So r0, and we can say that sigma theta theta depends on r only, right? So this means we need to check only r equation of equilibrium. Equation of equilibrium in r direction. If we check equation of equilibrium in our direction, so this is given by del of sigma r over del r plus 1 over r del of tau r theta over del theta plus del of tau r z over del z plus sigma r. So this is the extra term sigma r over minus sigma theta theta over r equal to 0. Right? So this term is already 0 because stress to r theta is 0 and to r z is also 0. So this term is also 0. And only left are these terms, these three terms. So in these three terms, if we differentiate del sigma r over del r, so you get minus b over r cube. So I'm writing here. This is minus b over r cube plus sigma r over r. So this will be a over r minus b over r square. And minus of sigma theta theta over r. So sigma, so this will be plus actually. Yeah. So minus of sigma theta theta over r. So this will be 1 over r. So this will be a over r. This will be r cube actually. And minus b over r cube, right? So this we have to prove that it should be equal to 0. So let me just prove that. So b over r cube. This b over r cube will get cancelled with this one. These two will get cancelled. Uh, well, I'm using this shape. Here this differentiation of this will be minus 2b over r cube, not minus b over r cube, because that was b over r square. So this will be minus of 2b over r cube. Because if you differentiate this with respect to r squares, you'll get minus 2b over r cube square. So let me just expand it. So here you have minus 2b over r cube. And you're able to see that it will be 0. Here you have minus a over r plus b over r cube. So these two terms will get cancelled, a over r and minus a over r. And this b over r cube plus b over r cube will become minus 2b over r cube. So these will also get cancelled. Similarly, I mean, that's why you have proved that the stress field satisfied equilibrium equations. Now in the part B, you have to find the stress vector on a cylinder surface at r is equal to a. To find stress vector, firstly, we need to find the unit normal. Firstly, you need to have stress tensor, and then you need to find a unit normal of that surface, and then you can find stress vector on that surface. So let me write about the unit normal. So the unit outward normal vector to a cylindrical surface at r is equal to a is, so n is given by, and out, since this is outward normal vector, so this will be nothing but er only in radial direction, right? And the traction vector on this surface, right? On this surface, you need to find out traction vector, and this radius is r is equal to a. So the traction vector will have three components, obviously. So this will be noting as tr, t theta, t theta, tz, right? And so this will be the traction vector, and this will be given by the stress tensor is sigma rr and sigma theta are non-zero, other terms are zero. And then you need to find out, so that will be traction will be sigma times n is er. So er will be nothing but r r theta z. So r will be 1, theta will be 0, z will be 0. So if you now expand this, so finally solve this, so you'll get this as sigma r 0 0, right? So it means your traction vector, three component of traction vector is TR is equal to ER sigma RR, and obviously the sphere components will be zero, right? So sigma RR, you already know what is sigma RR. So, so if you write traction vectors, that is TR ER plus E theta E theta plus TZ EZ. Right? So TR ER, so the last two terms are zero, so when you have TR ER, so means sigma RR ER. Sigma RR ER, sigma RR is nothing but A plus V by R square, and R is equal to A in this case, so A plus V by A square. So this will be a traction vector on a surface with radius R is equal to A. Now in part C, you need to find out the value of capital A and capital B, where boundary conditions are given to you that at inner radius you have uniform pressure Pi, and outer radius you have zero traction. Okay, so let me just find out. So you have the boundary conditions. The boundary conditions are given as at R is equal to R naught. It is given to you that at R is equal to R naught, we have found out that traction vector at some radius and any radius will be sigma RR only. So at R is equal to R naught, traction is given to be zero. It means sigma RR will be zero. And at R is equal to Ri, your traction is given to be minus of Pi, right? Minus because on the inner surface, your ER will be minus ER because your outward normal will be towards inside. It will not be actually on the inner surface. There will not be outward normal, but it will be inward normal. So that will be in minus ER direction. So that's why it will be minus Pi times ER. So you can just say that. So that's why I've taken minus Pi. So and sign has been used on this. Okay, so this is fine. So now you can easily find it out because you have two constants in sigma r and you have two values of sigma r. So let me firstly put this condition, first condition. If you put the first condition, so sigma r is a plus b by r square, so a plus b by r outer square, that will be zero. And the second condition is a plus b by r inner square, so that will be minus of b. The minus you would have understood because this will be minus of pi into er. Actually, minus is coming into er because er here is upward normal, inward normal vector. So that will be minus er. So this this writing like this one. Now if you try to solve this, so find a, you can just simply what you can do simply subtract these two equations, so you get v over r naught square minus v over ri square is equal to minus p plus p actually. Yeah. So because I have subtracted second equation from the first equation, so you can take v as common, and so finally you will have pi r naught square ri square over ri square minus r naught square. Right. Yeah. So this will be your b, and it will be negative because ri square is less than r naught square. You can write like this also. So v will be pi minus of pi r naught square. So this is ri square over r naught square minus ri square. And if you substitute in equation one this value, so a will be minus of b by r naught square. So we get a as positive. So this will be pi times ri square over r naught square minus ri square. So this will be the two terms. Okay. This is the final equation. This is the value of b and this is the value of. Let me just download this. So let me go to the next question. There is problem number 4. In this problem, what you need to do is, let me just write P4. So in this problem, you have to think of isotropic solid cylinder. Think of an isotropic solid cylinder, which is glued to a rigid plate at both its ends. Okay, and then it has been given the two rigid plates are then pulled against each other, pulled apart along the axis of the cylinder. Along the axis of the cylinder. It turns and it is pulled such that the normals of the rigid plate remain aligned with the axis of the cylinder. So it has been pulled such that the normals of the rigid plates remains aligned with the axis of the cylinder. Turns out that u naught u theta is 0 in this case, but ur and uz do arise. ur and uz will be there, but u theta will be 0. Furthermore, UR and UZ are not functions of theta coordinate. So you have to assume that the deformation of the cylinder is such that every planar cross section of the cylinder you can say Z plane or axial planes. Planar cross section of the cylinder will be Z plane. Z is along the axis of the cylinder. So every planar cross section of cylinder remains plane after deformation. The planar cross section remains plane and then remains normal to the Z axis. Okay. And the rigid plates also remain normal to the Z axis. But it does change the radius. The radius of the planar cross sections will change. So simply you have like this cylinder and there are two rigid plates attached across the ends of the cylinder. Now you are pulling these rigid plates apart such that these rigid plates will remain normal to the z-axis of the cylinder. The cross section of the cylinder will also remain normal to the z-axis, but the radius of the cylinder will decrease because if you're pulling apart due to Poisson effect, the solid cylinder radius will decrease. Now what you need to find out is in part A, you have to find what can you say what can you say about the dependence of UR and UZ and UZ on radial and axial coordinates. Obviously, it is given that they are independent of theta, but you have to comment on whether this will be a function of R and Z or not. Second, we have to obtain the strain matrix and the stress matrix of the above equation. In part C, you have to show that the theta component of stress within equation is automatically satisfied. Right? And part D, you have to tell what boundary condition will be used in order to solve the above equation, in order to solve the above deformation problem. Okay, let's start. So let me draw the diagram of the cylinder. So cylinder is like this. We have a radius here and radius here. These two are connected, and these are connected through some rigid plate. So let's say this is the plate here, and this is the plate here. Okay, so and let's say center at the center you have here as z coordinate, and here it's going to you that this is L by 2 and this is also L by 2. So and you're applying, you're filling these two rigid plates apart. Finally, if you pull these two rigid plates apart, so the cylinder will become like this. It will be something like this, right? Let me draw it nicely. So this will be uniform. So it will be something like this. Okay, so and let's say obviously there will be some stretching. It will not be exactly here at this point. It will go up to, let's say here, it will go up here. Okay, it will go up here. So let's say this amount of stretching is there. So this is known as delta amount of stretching from here, delta from here, and obviously this will be to here to be L by 2, and this is again to be L by 2. So can say that this is prescribed displacement, amount with which you are stretching. So it is already defined. It is already known. Okay, it is prescribed. So let me go to the solution part. So in the first part, you have to say about dependence of UR and UZ on radial and axial coordinates. So if you see here, UR, if you are able to imagine, UR is the deformation of the cylinder along R direction, and UZ is along axial direction. So and U theta is 0. It has already been given. So you are able to see that UR will be dependent on Z, right? Because at this point, your radial compression is more, and here radial compression is less. So your UR, that is radial deformation, is a function of Z, that is for sure. But your UR is also a function of, although this is UR may be function of R also, because this is a thick cylinder, right? Maybe it may be thick or thin, but if it is a thick cylinder, UR may vary with radius at a particular Z. Okay. Now talking about UZ, that is axial stretching. So axial stretching will be a function of Z for sure, because here axial stretching will be different, here it will be different, here it will be zero actually, because it is being stretched from here and here equally. So axial stretching will be a function of axis, axial coordinate, that is z, but axial system won't be function of r, because it has been said in the question that plates plates are normal to each other. So each cross section, if we cut a cross section, so each point in that cross section will have equal amount of axial stretching. So from here we can conclude that, let me just write, due to extension of cylinder and the ends of cylinder are glued with rigid plate. Therefore, the radius of cylinder will change non-uniformly. Non-uniformly means at different z you will have different radius of cylinder. So we can say that from here, so ur is a function of z. Ur will also be function of r. You can say that ur will also depend on r, because it is a solid center, so it will be obviously radial displacement will be zero at the center, right? So okay, so it will be thick only because solid cylinder. It will be thin also, but yeah. So at the center, ur will be radial displacement will be zero, and there will be some radial displacement when you have some finite radius. That's why it's varying across r. So also depend on r, because okay, ur is zero. So I can write that it is zero at r equal to zero, but it's non-zero. It is non-zero for other values of r. Also, use it. We write about use it. Also, use it does not depend on r because of the conditions given in the question. It will be function of, it will depend on z only. From here, we can conclude that ur is a function of r and z both, whereas uz is only a function of z. So in part B, you have to find the strain matrix and stress matrix. So let me write the strain matrix. The strain matrix in cylindrical coordinate system, that is given by del ur by del r, and then you have 1 over 2 del ur by del theta plus del u theta by del r minus u theta by r, and then you have 1 over 2 del u r by del z plus del u z by del r, right? And then here you have 1 over r del u theta by del theta plus u r over r. And then here you have half of del u theta by del z plus 1 over r del u z by del theta. And then here you have del u z by del z, and rest of the matrix is symmetric. First term will be there, it will be non-zero. But if you see the second term, so since u theta is zero and no variable is a function of theta, so then u r by del theta will be zero because u r is not a function of theta, and u theta is given zero in the question. This will be zero, and this will also be zero. Similarly, del u r by del z. So this will be non-zero, but del u z by del r, because u z is not a function of r, so this will be zero. Similarly, here also u theta is zero, and here in the next term, here also you have u theta 0, and uz is also not function of theta. This will be 0. So you will be left with these terms here. Let me rewrite. So, you will be left with del u r by del r 0, 1 over 2, del u r by del z 0, u r over r. This will also be 0. So this is symmetric, so this will be 1 over 2, del u r over del z. This will be 0, and then this will be z. This is your strain matrix. And stress, you know that it is given by, for isotropic material, it will be lambda times space of m del ij plus 2 mu epsilon ij. So similarly, you can just find sigma rr is equal to lambda times space of epsilon will be summation of the diagonal terms. So then u r by del r plus u r by r plus then u z by del z, and then 2 mu epsilon z epsilon rr. So epsilon rr is del u r by r, del r, right? This is sigma r, and then we have sigma theta theta. So that was again this trace of epsilon will remain same, then u r by del r plus u r by r plus then u z by del z plus 2 mu. Here you have epsilon theta theta. So epsilon theta theta is what? That is u r by r, right? This is epsilon theta theta. Now you have sigma z z. So sigma z z is lambda times this trace will remain same plus 2 mu del u z by del z. Right. Now you have tau r theta is equal to 2g times epsilon r theta. So epsilon r theta is 0. So that's why this will also be 0. Then, because from here you can say that this is epsilon r theta, right? So this is 0. That's why this will also be 0. And then we have tau rz. So that will be 2 times g and epsilon rz. So epsilon rz is what from this? So this is epsilon rz 1 by 2 del u r by del z. So 2 and 2 will get cancelled. So you will get g times del u r by del z. Right? And then finally you have tau theta z. So this will also be 0 because epsilon theta z is 0. So epsilon theta z is which this term. So this is 0. That's why this will also be 0. And then you have to in part C what you have to do. In part C you have to show that the theta component of stress equilibrium equation is automatically satisfied. So let me write stress equilibrium equation in theta direction. So that is this is del of tau theta r over del r plus del of sigma 1 over r del of sigma theta theta over del theta plus we have del of tau theta z over del z plus extra terms are there. So this will be to twice tau r theta by r. So that is extra term. And restrictions, body force is not present, and acceleration is also not present. So this will be 0. Now you have this tau theta r is 0. So this term will also be 0. Sigma theta theta, and you have this term. So, but sigma theta theta is not dependent on theta because ur is not dependent on theta and uz is also not dependent on theta. So this will also be independent of theta. So again, this term is 0 because it's not dependent on theta. So differentiation of this will be 0 respect to theta. And tau theta z will be 0. So this will also be 0. And again, tau r theta is 0. So this term will also be 0. So that's why this uh, stress equilibrium equation in theta direction is already set, automatically satisfied. Now in part D, what you need to do? In part D, you have to find what boundary conditions will be used in order to solve the above deformation problem. So boundary condition that will be used, you're able to see that at z is equal to minus L by 2. What boundary condition you have? So you have uz present. So uz is prescribed. So here at z is equal to minus L by 2 and any across the whole cross section, you have prescribed uz that is delta, right? So at z is equal to minus L by 2, you have delta, uz as delta, and at z is equal to plus L by 2 also, you have uz as delta. So both uz is prescribed. And at z is equal to minus L by 2, you have ur will be 0 uh, because this cross section is glued to this plate and this plate is rigid. It is neither expanding in this direction nor contracting. Across in the plane of the plate, it is neither contracting nor expanding. So that's why here also there will not be any radial deformation in this cylindrical body. So that's why here ur will be 0 and z is equal to minus L by 2 and plus L by 2. Okay. And then this top surface will be traction free. So at r is equal to r naught means outer surface. So traction will be 0 means your sigma rr will be 0. Okay. And that's all I think. So this will be the boundary conditions. Let me just write these boundary conditions. So the boundary conditions along the four edges of RZ plane are so in this problem, how many stresses are there? Which are 1, 2, 3, 4, 5. So all these stresses are depending on UR and UZ only, right? So there are two deformation fields that you need to solve. Okay. So and those are functions of R and Z. UI is function of R and Z, UZ is function of Z. Okay. So let me just write the boundary conditions. So at Z is equal to L by 2, I'm firstly writing. So at Z is equal to L by 2, you have radial displacement will be 0, right? So radial displacement at any R, at any radius, and Z is equal to L by 2, so that will be 0. And obviously prescribed, this UZ will be prescribed. So UZ at Z is equal to L by 2, which will be delta, right? Then you have at Z is equal to minus L by 2. So at Z is equal to minus L by 2. So what do you have? So UR is again 0 and UZ is again prescribed. Then you have some boundary condition at radius is equal to 0. You have one more thing that at radius is equal to 0 and radius is equal to 0, UR will be 0 because central line of this solid cylindrical body, the axis will not have any radial deformation. It will because it is a symmetrical deformation in terms of radius. So there will not be any uh, radial deformation of the axis of the cylinder. It will be at its place only. It will not get displaced. So you can say that you are at r is equal to 0 at any z will be 0. And then you have at r is equal to capital R, that is outer surface, your traction force will be 0. This will be traction free. You can just find, I was saying that sigma RR will be 0, but obviously that is one component of traction. Similarly, you have R theta and RZ also. So that also will be, that will be traction free and destructive. So we'll stop here for today. And if you have any questions, you can ask now. Please ask if you have any question. Okay, so we'll stop here and we'll meet in the next week.